Last time we looked at the HOM functor, which takes a bunch of contracts and produces a contract. The contracts it takes describe the inputs and output of a guarded function. This contract here, result, expects a function and then wraps these contracts around it. Before is the contracts for the input, after is the contracts for the output, and so this result, so this one takes middle and produces a guarded function that wraps middle by checking the input contracts and then applies middle and then checks the output contract with some extra JavaScript guff for making it all work nicely around objects and to print nicely. Using HOM, we can then write our function without mentioning any contracts in the body, and we can put the contracts right up front, so when we look at the definition we can see what the types ought to be right at the very beginning. We don't have to go hunting around in the body of the function to find what contracts they're trying to apply. And here's an example where we don't have any inputs, we only have the output contract. And so, of course, this function takes no inputs. Today we're going to talk about something called monoids, and then see how to use HOM to describe them. So a monoid is a set equipped with a binary operation, it's associative, and an identity element. So let me give you some examples. Say we've got these strings, hi space, or let's do it this way, hello space, comma space, world. Okay. So when we add these, that is when we concatenate them, we get hello, comma, space, world. Nothing very complicated. This is our binary operation. It's concatenation. Okay. Now we said it has to satisfy some constraints. One, it has to be associative. That means if I type quote A plus quote B plus quote C, that should be the same thing as quote A plus then quote B plus quote C. Oops, close bracket. And of course this holds. Both of them are the string ABC. Right? So it's associative. That satisfies one of the conditions. The other condition is that it needs an identity element. So the identity element is, of course, the empty string. So it doesn't matter whether you concatenate it on the left or on the right, we get the same value A. Okay. So concatenation is a monoid. It has a binary operation that is associative and what they call unital. It has an identity element. Okay. How about another example? Plus as used on numbers. So 5 plus 6 is 11, right? Doesn't matter whether we do 5 plus 6 in parens plus 7, or if we do 5 plus paren 6 plus 7. It is associative. And it has left and right unit. 0 plus 5 equals 5. 5 plus 0. Right? Left and right units. Notice this one is commutative. It doesn't matter whether I do 5 plus 6 or 6 plus 5. This one certainly is not. A plus B is not B plus A with strings. So commutativity isn't part of the definition of a monoid, just associativity. We also have a monoid for multiplication. 5 times 6 is 30. 5 times 6 times 7, parenthesized on the left, is the same as 5 times 6 times 7, parenthesized on the right. Now the identity is, for multiplication, is 1. 1 times 5 is 5 times 1. So here again we have a commutative monoid, but commutativity isn't necessary. To emphasize that, suppose we have guarded functions from a contract C to itself. So for example, guarded functions that take in an int32 and put out an int32. Well, if I have f of g of h of x, here my operation, well, let me write it this way. Function, write this compose function. Function compose f and g, return function x, return f of g of x. Great. So now here is a binary operation. It has 2 parameters. It's associative because compose fg, compose h is the same thing as compose f compose gh, because they're both function x return f of g of h of x. These two give the same answer. Those 3 things stuck together. So composition is an associative binary operation, and of course it has an identity. Function of x return x. So if we stick in the identity for f and h, we're just going to get g. Right? If I stick in the identity for f here, I get g. If I stick in the identity for g, I get f. So composition of functions, guarded functions from one contract to itself form a monoid. And we clearly can't swap these two. F applied to g of x is not the same as g applied to f of x in general. So here we have a bunch of different examples of monoids. We'd like to be able to capture that notion, a binary function that's associative with an identity element. So here's how we're going to use HOM and products in order to create something that's kind of like an interface that will be useful in writing monoids. So we need a set of elements. We need our associative binary operation, and we need an identity element. Now I'm going to write this as a function that takes no inputs and produces an element. So let's look at this part here. So first we're going to create a product indexed by strings. The 3 strings are t, times, and 1. Okay, so this thing is going to create a contract, and then we're going to apply it to this object and return the result. So the result is going to look a lot like this object. It will behave identically to this object, except that it will have contracts. So here, T is the contract func. So it says, whatever you supply me for a set, since you're putting it there, set had better be a function. In fact, we're going to supply a contract. Whatever you supply me for times had better be a function from two elements of the set to an element of the set. So here he passed in a contract, and here it's saying the two inputs both need to pass that contract, and the output also needs to pass that contract. So if this is strings, well, str is a function, good, and what you supply for times, concatenation, should be a function from two strings, the one on the left and the one on the right, to one string, the resulting concatenated string. And the identity should be a function that supplies me with a string. Okay. So now we can say var stir monoid is monoid of stir. Times is going to be the concatenation, so function x, y, return x plus y, and function nothing, return the empty string. Oops. Great. Now notice here I didn't say x and y were strings. That gets taken care of because this contract gets applied to this function. The contract wraps up this function in these guard contracts. And that's what I get as the result. So then I can say things like stir monoid times, well, let's log this, console.log cross fingers, hope expected a string. What expected a string? We got something else being run up here. Ah, there it is. There we go. Hello world. So it looked up the concatenation operation and applied it to hello and world. Now notice here that I haven't verified that times is associative. And I haven't verified that this is an identity. In general, this problem is undecidable. You can't write a program that verifies it. So the way that programmers in general have come up to deal with this problem of undecidability is to write tests for small cases. and hope that if your implementations are simple enough and you test the simple enough cases and the boundary edge cases of the simple things, that when you assemble them together, they will still behave in the way that you expect them to. So, whereas the mathematical definition of a monoid said, I need a set of items with an associative binary operation and an identity element such that this thing is unital. That is, when we apply it to the identity, we get the same thing back. In computer science, we can only say this is a binary operation, this is a nullary operation, and you should write tests for the monoid. So I could do something like if you give me a monoid and 3 elements of the monoid, we should say mon.t of A, mon.t so A, B, and C should be elements of the monoid. And it should be associative. If this thing is not equal to this one, no new for not associative. So here, if you generate random A, B's, and C's, A's, B's, and C's, then this thing will check if it's associative and throw an exception if not. And so then your tests can check some finite number of elements of your monoid. Note this will fail if we try and do the function composition monoid, because what we get back is an object rather than a primitive type. So objects compare by reference rather than by what they actually do. And so if we were composing functions rather than multiplying numbers or concatenating strings, this wouldn't work. So then you'd have to supply a bunch of inputs to the function and check if those inputs differed between the two. And so it becomes even harder to check. But you do what you can. So here's the signature of the monoid, the binary function and the nullary function that provides the identity. And then you write tests to cover the relationships between those as best you can. So here I had the string monoid. You can write another one, var int32 monoid. Actually, let's call this addition. We should actually call this concatenation, because that's really the fundamental operation of this thing. It's a monoid in 32. Actually, we can just use num. That'll work. Function xy, return x plus y. Function return 0. So now we can do addition. And then say 5 and 6. Run it. Get 11. Great. So this idea of using a product indexed by strings to wrap up a set of operations and a contract on the allowed elements, followed by implementations of those, is a pretty useful pattern. You can do all of what's called universal algebra this way.